Good afternoon, everyone. I would like to thank the Dean, Subit, and Jennifer for taking this great initiative in our college. I would like also to thank the audience for attending this seminar. Today, I'll be talking about our recent research on developing a smart left decision support system for flashing yellow arrow signals. First, I would like to give a little bit of background about myself. My name is Hatem Abou-Senna. I'm an assistant professor in the civil engineering department. I graduated from Cairo University in Egypt in 1993. Then I came to UCF in 2001 to get my second master's degree. I worked in the private sector for about 5 years and then joined UCF again in 2009 to complete my Ph.D. And then I worked as a postdoc for a couple of years, and then in 2014 I became an assistant professor. My primary research is focused on the operational and behavioral aspects of the traffic system, considering advanced traffic control devices, left turn signalization, smart corridors, and intelligent intersections. I'm also interested in pedestrian and bicycle safety, as well as air quality impacts. I teach the traffic engineering graduate course. I actually love this course, and I believe it's the cornerstone for all the fundamentals and concepts leading up to the current connected and autonomous vehicles research. In terms of key achievements, I'm a member of the UCF Sustainability Working Advisory Team, SWAT Committee on Transportation, which focuses on achieving carbon neutrality by year 2050 and improving mobility on campus. And one of our key achievements in 2017 was to get UCF recognized nationally as a bicycle-friendly campus by the League of American Bicyclists. I was also among the team that introduced bike share program in 2018 and selected line bikes. In terms of research, we received the Best Project Award from ITE, Pedestrian Bicycle Committee, on a pedestrian bicycle safety project sponsored by the Florida Department of Transportation. And it was very crucial because at that time, the state of Florida was reported to have the highest 4 pedestrian fatality locations in the country, with Orlando topping the list. So we developed a safety prioritization tool, which enabled the state to target like specific areas with the most urgent needs at these locations. I also developed a microscopic transportation emissions model, MicroTEM, as part of my PhD, which integrated a microscopic traffic simulation model, VSIM, with the latest Environmental Protection Agency MOVES model. I actually keep getting several requests from other universities to use the model and help them in their research. So from California Polytech University, Carleton University in Canada, University of Texas, Arlington, and University of Dayton. The Flashing Yellow Arrow Signal project is another key achievement in my career, as it was recognized locally and statewide. I will talk about it and the Express Lanes project in the next slides. I'll go over a couple of projects before talking about the Flashing Yellow Arrow, just to give you a feel of what I do. For example, this project is about the impact of distracted drivers and pedestrians on signalized intersections. I just want to mention that this is still an ongoing project. As you can see, it started right before the pandemic, and at the time we were supposed to collect data from the field. The lockdown happened, and because there were no cars on the road, we couldn't collect any data, and we were delayed and behind on schedule a little bit. So this project addresses the new Florida laws related to prohibiting cell phone use while driving, but it's still allowed when the vehicle is stationary, which is probably going to be during the red phase of the traffic signal. The uniqueness of this project is to measure distraction from the field in real time. We actually found that all previous studies were either survey-based or lab-controlled experiments putting cameras in specific vehicles to measure distraction, which can be biased. As you can see, we are using a solar-powered trailer with 2 high-resolution cameras to monitor the intersection approach and the signal changes. The outcome of this project will determine whether additional laws are needed to prohibit cell phone use or recommend other policy decisions. So this video shows an example of a distracted driver using her cell phone and we need to determine like how this additional lost time added from distraction can reduce and affect intersection operations and capacity. Another project is related to the color of delineators which separate the express lanes from the general lanes, such as the one on I-95 near Miami, if you're familiar with it. The main issue is that DOT replaces about 6 to 8 of them, the delineators on I-95, every week, costing them over $1 million a year. Also, the current color is orange. And as you can see, the color can be visible if it's in good condition and can be completely faded during dust time. So it's a human factor issue that is directly related to driver's perception and reaction time, as well as a maintenance issue. So we developed a driving simulator experiment with a 6-mile section of the I-95 and invited about 180 participants with different gender and age groups. The experiment included the effect of daytime versus nighttime, high and low visibility, roadway surface type, whether concrete or asphalt, because of the contrast between the colors, along with 5 different colors approved from the Federal Highway Administration. The results showed that the white color was the most noticeable color in majority of the scenarios, followed by the yellow color. And it was actually, we did like, we collected data from the driving simulator, as well as an exit survey from the participants. And actually the data matched that the yellow was the most noticeable color for them, followed by the yellow color. The key achievement of this project is that the upcoming edition of the MUTCD, the Manual on Uniform Traffic Control Devices, which is a nationwide standard for the 50 states, will change the color from orange to pavement marking colors, which are the white and yellow colors based on this step. Moving on to the flashing yellow arrow. Just want to mention that the idea of this project started when the flashing yellow arrow became the new standard for signalization for left turns. And but the majority of the intersections were still using the old 5-section head. I believe most of you are familiar with this configuration. We call it the 5-section head. So it has 5 displays. The left green arrow is we call it a protected phase, while the green ball is the permissive phase, where you can make the left turn, but you have to yield to oncoming traffic and find a sufficient gap to make the turn. This is actually one of the most dangerous movements a driver can make as you are traveling across opposing traffic lanes with high speeds. The issue is that, as you see, it's green, and we have a lot of tourists in Florida. And if you don't understand, some people think that because it's green, it's your right of way, but it's not. Compared to the flashing yellow arrow, everybody understands anything yellow and flashing, you have to be cautious. So the 5-section head has several issues, and one of them is that it's shared with the through movement. So the green ball is mainly for the through movement, the through traffic, but at the same time, we can make the left turn if we can find the gap in the opposing traffic. The problem is that it may not be utilized, either because there's not enough gaps to make the turn, or maybe there is heavy pedestrian activity. So if there's a concern with the permissive phase during certain times of the day, let's say school arrival and dismissal, and we need to modify the display during that time, we actually have to replace the whole signal, even though it's only needed a few hours per day. So the flashing yellow arrow overcomes this limitation. It is separated from the through movement, exclusive for the left turn, and the display now can be protected only, permissive only, or a combination between the two. One of the major objectives of this project was to be able to communicate with various traffic controller types. In Central Florida, we have about 3 or 4 different controller types, and we wanted this technology to be compatible across multiple systems. We first tested it in a controlled environment at UCF lab using peer-to-peer logic. As you can see here, we used traffic signal cabinets with the different controller types: Siemens, Econolite, Nasdaq. We used an actual 4-section head display, CCTV cameras connected to a computer to monitor intersection traffic flow, a data logger device to receive detection from the field, and a custom communication software to display real-time status of the field data. As you can see here, the peer-to-peer logic, like the vehicle detection is sensed in the field from loops or video detection. Then it is mapped in real time to the controller in the lab. The algorithm analyzes the traffic data and then makes a decision that is communicated back to the controller. And this is like a safe environment to as a proof of concept before actual implementation in the field. The other main objective is to know the best times of the day to efficiently use the flashing yellow arrow. Flashing yellow arrows are programmed by time of day, but the methodology used is based on a snapshot of the peak period. And then the rest of the day, these drivers are penalized based on those 4 to 6 hours, which is only like 25% of the time when you compare it to 24 hours of the day. So 75% have to abide by those 4 to 6 hours. And so the signal may be a red arrow for a 12-hour period when the traffic volumes are high, but that doesn't account for the gaps in the traffic during this long period. So we developed a new technology to make flashing yellow arrow signals much more responsive to fluctuating traffic conditions, with guidelines to activate or deactivate the flashing yellow arrow. The idea was to predict the traffic behavior in the short term based on historical data of the past few cycles, using a moving average window to predict the behavior of the following cycle. The algorithm determines the time interval between successive arrivals of opposing vehicles for each lane by cycle on a second-by-second basis. And then this headway is checked against the minimum acceptable gap thresholds database that we collected from the field. We actually collected like 30,000 cycles from the field, and based on that, we developed our minimum thresholds by crossing 1 lane, 2 lanes, 3 lanes, or 4 lanes. If the minimum headway is achieved, then the decision is to switch to a flashing yellow mode. Otherwise, a red arrow is activated. The final step of the project was to install and test the DSS in the field. So the system was tested at 6 intersections in Seminole, Orange, and Volusia counties. We also wanted to examine the sensitivity of the DSS. So the testing period was chosen from 2 p.m. to 5 p.m. to account for off-peak period and the transition into the peak period, which is a critical one. So you can see here, this table provides a summary of the log file and the DSS decisions in each cycle during the testing period. When there are enough gaps exceeding the threshold, a flashing yellow arrow is activated. You see, approaching the peak hour, the gaps started to diminish, and the algorithm decision was red arrow, except for a couple of cycles where there's enough gaps detected. I would like to show you this video covered by Channel 9. We'll give you an overview of the developed system.
UCF researchers say they've built a better, safer left-hand turn signal system.
And you may already have tested it as part of your drive around Central Florida. Channel 9 anchor Jamie Holmes shows us the new system aims to make sure left turns are treated right.
Making a left-hand turn with a green arrow is easy when there's lots of traffic, but when there are no cars and you have to wait and wait for that green arrow, it can be frustrating.
There are times where the traffic maybe is not so heavy and people are sitting at the red arrow and they're going, come on, can this thing change?
In fact, when it comes to complaints to FDOT, the left turn signal is a regular one, so they turned literally to UCF, which has designed a decision-based left turn signal system. It uses technology already at intersections, the pre-existing ground sensors in the road, which detect vehicles and trigger lights. When there's enough delay in passing vehicles, the red arrow switches to a yellow flashing one, allowing the driver to make a left-hand turn.
And it calculates the enter-arrival time, or like the gap between arriving vehicles. We can determine whether it's safe now to cross, or like we have enough gaps.
And it's a simple fix. It's just an algorithm. UCF has tested it at their lab on campus, where this traffic cabinet sits, controlling intersections you're using right now.
Because we have fiber optics from DOT and we have a switch in this room that it's communicating between the two, like controls the one in the field and the one in the lab.
The data has been turned over to FDOT, which will assess whether to make this change statewide. So in the future, if you turn left on a flashing yellow arrow, UCF may have paved the road.
There are things that involve science
and tweaking that, we have to rely on others who have the expertise and the scientific backgrounds. And that's why we turn to UCF to help us on this.
In Orlando, Jamie Holmes, Channel 9 Eyewitness News.
So I hope this video clarified the whole approach. So in terms of future research, we are anticipating a couple of projects, especially a before and after study for the flashing yellow arrow at dozen intersections, which will help us develop best practices and guidelines to be implemented nationwide in the MUTCD. There's another project on innovative safety messages. If you notice now on the highways, the variable message signs display messages like speeding costs money, and speeding wrecks your day, instead of like the traditional slow down or buckle up. So they wanted to study their effectiveness, and it will be a collaboration between UCF, Institute of Simulation and Training, Psychology Department, and F.D. In the long term, I'm looking for collaborations to expand on connected and autonomous vehicles research related to signal phasing and timing applications, connected infrastructure, as well as improving transit through the concept of mobility as a service. And hopefully also continue with our main goal to achieve carbon neutrality on campus. Finally, I would like to acknowledge my research team of undergrad and graduate students, all civil engineering faculty, and especially the flashing yellow arrow team from F.D to Orange, Seminole, and Volusia counties. And thank you for your attendance.